When a router first powers on, it knows almost nothing. It can see its directly connected interfaces, the cables plugged into it, the networks immediately attached. That's it. It has no knowledge of what lies beyond its immediate neighbors, no map of the wider network. And yet, within minutes, sometimes seconds, that same router can be correctly forwarding packets to destinations thousands of miles away, through networks it has never explicitly been told about. It learned, automatically, continuously, by communicating with the routers around it. The process by which routers go from knowing nothing to knowing enough, and by which that knowledge stays current as the network changes, is what this video is about. Route discovery and propagation are the engine underneath the routing table. Without them, the table is empty. With them, the table becomes a living, updating map of the reachable world. Let's start with the simplest case, because it's instructive even though it doesn't scale. A network administrator sits down and manually types routes into every router. To reach this network, send packets here. To reach that network, send packets there. Every entry explicitly configured by a human. This is static routing, and it's perfectly appropriate for small, simple, stable networks. But static routing has a fundamental problem. It doesn't adapt. If a link goes down and a path becomes unavailable, the static route pointing through that link stays in the table. The router keeps trying to forward packets down a path that no longer works because nobody told it the path is broken. A human has to notice the failure, log in, remove the broken route, and add an alternative one, manually, while the outage is ongoing. For a network with 5 routers, this is manageable. For a network with 500, it's untenable. For the internet, with hundreds of thousands of routers operated by thousands of different organizations, it's simply impossible. Dynamic routing exists because networks change, and humans can't keep up. In dynamic routing, routers don't wait to be told what's out there. They discover it themselves by running a routing protocol, a standardized language for exchanging routing information with neighbors. The basic idea is straightforward. Each router tells its neighbors what it knows. Its neighbors incorporate that information, combine it with what they already know, and share the combined picture with their neighbors. Knowledge propagates outward, hop by hop, until every router in the network has a complete enough picture to forward packets correctly. When the network changes, a link fails, a new connection comes up, a router is added or removed, the change triggers an update. New information flows outward from the point of change, updating routing tables as it spreads until the entire network reflects the new reality. But there are fundamentally different approaches to what routers share with each other and how they compute paths from that information. Understanding those differences is the key to understanding the major routing protocols and why different protocols are used in different contexts. There are 3 main families: distance vector, link state, and path vector. Distance vector protocols are the oldest and conceptually simplest approach. The name describes exactly what routers share with each other: their distance to various destinations and the direction, the vector, to reach them. In a distance vector protocol, each router maintains a table of destinations and the cost to reach each one. Periodically, it shares this table with its directly connected neighbors. A neighbor receives the table, looks at each entry, and thinks, if I can reach my neighbor at a cost of X, and my neighbor can reach destination Y at a cost of Z, then I can reach destination Y at a cost of X plus Z. It updates its own table accordingly, then shares its updated table with its own neighbors. The process repeats, spreading knowledge outward. This is sometimes called routing by rumor. Each router is trusting what its neighbors tell it, without any direct knowledge of the full network topology. I don't know the full path to destination Y. I just know that my neighbor says it can get there in Z hops, and I trust that claim. The classic distance vector protocol is RIP, the Routing Information Protocol. It's simple, easy to implement, and works fine in small networks. But it has a well-known weakness. It reacts slowly to failures, and under certain conditions, it can produce routing loops where packets circulate between routers that are each incorrectly believing the other has a valid path. Just note that routing by rumor has a cost. If a neighbor's information is wrong, your decision based on it is also wrong, and you might not find out quickly. Link state protocols take a fundamentally different approach. Instead of sharing distances and directions, each router shares its direct observations of the network, what links it has, what neighbors it's connected to, what those connections cost. Each router shares its own local view, not its computed conclusions. Every router in the network collects these local observations from every other router, assembling them into a complete picture of the entire network topology. With the full topology known, each router independently runs a shortest path algorithm, typically Dijkstra's algorithm, to compute the best path to every destination. Every router does this calculation itself, using the same complete topology map. This approach has significant advantages. Because each router has the full topology, it can compute paths independently rather than relying on its neighbor's conclusions. If a link fails, the router that directly observes the failure broadcasts that observation to every other router in the network immediately, not passing it neighbor to neighbor like a game of telephone, but flooding it out to everyone at once. Every router updates its topology map and recomputes its paths. The response to change is fast and accurate. OSPF, Open Shortest Path First, is the dominant link state protocol in enterprise and ISP networks. It's more complex to implement and configure than RIP, requires more memory and processing power, and generates more traffic between routers during topology changes. But it converges faster, handles failures more gracefully, and doesn't suffer from the loop-prone behavior that plagues distance vector protocols. For any network of meaningful size, link state is almost always the right choice over distance vector. Both distance vector and link state protocols are designed for routing within a single organization's network, what's called an autonomous system, or AS. They assume a degree of mutual trust between all the routers running the protocol. They optimize purely for technical metrics, hop count, bandwidth, delay. They have no concept of business relationships, policy constraints, or the fact that the network extends beyond the organization's own infrastructure. But the internet is not one organization's network. It's a collection of tens of thousands of autonomous systems, each independently operated, each with its own internal routing, that need to exchange routing information with each other. And routing between autonomous systems requires something neither distance vector nor link state can provide: the ability to express and enforce policy. This is where path vector protocols come in, specifically BGP, the Border Gateway Protocol. BGP is the routing protocol of the internet. It's what makes it possible for your ISP's network to know how to reach Google's network, and for Google's network to know how to reach a small regional ISP in Eastern Europe, and for that ISP to know how to reach everywhere else. The key difference in path vector is what gets shared. Rather than distances or topology observations, path vector protocols share the complete sequence of autonomous systems a route passes through, the AS path. When a router advertises a route to a neighbor, it says, "I can reach this network, and the path goes through these autonomous systems in this order." This AS path serves two purposes. First, it's loop prevention. If a router sees its own AS number in a path advertisement, it knows the route loops back through itself and rejects it. Second, and more importantly, it gives operators the information they need to apply policy. An organization can look at the path and decide, "I don't want traffic transiting through that specific AS. Maybe for commercial reasons, maybe for legal ones, maybe for performance reasons," and reject or prefer routes accordingly. BGP is less about finding the optimal technical path and more about implementing the agreements and policies that make the internet's commercial ecosystem function. It's configured with explicit rules: accept routes from these neighbors, reject routes from those neighbors, prefer this path over that one, never advertise this network to anyone except these specific peers. The internet's routing system reflects its economics as much as its physics, and BGP is the mechanism that makes that possible. The common thread running through all three approaches is this: routing knowledge is built from the bottom up and maintained continuously. Distance vector protocols build that knowledge by sharing conclusions, each router trusting its neighbor's reported distances and computing paths from what it hears. Link state protocols build it by sharing observations, each router broadcasting its direct view of the network, so every other router can compute paths independently. Path vector protocols build it by sharing journeys, each router advertising not just that a destination is reachable, but the full sequence of networks a packet would traverse to get there, enabling policy decisions that pure technical metrics can't express. Each approach is a different answer to the same fundamental question. Given that no single router can see the whole network, how do you collectively build a picture accurate enough to route correctly? The answer, in every case, is communication. Routers talk to each other. They share what they know, they update what they believe, and from those constant, distributed, local conversations, a coherent global routing system emerges. That is route discovery and propagation. Not a single mechanism, but a family of approaches, each suited to a different scale and a different set of requirements, all solving the same essential problem of turning local knowledge into network-wide understanding.